Welcome to the Explainer. Okay, we are jumping right into the deep end today. Imagine you are sitting in the exam hall. The clock is ticking down. You flip open your past paper. Maybe it's a classic 9713 question, or perhaps you're tackling syllabus codes 0417, 0478, 0983, 0984, 2210, or the notoriously rigorous 9618. You look at the page, and the scenario they've given you just looks like a massive, impenetrable wall of rock. Well, I want you to meet two students who are staring at that exact same wall of rock. First, we have Alex. Now, Alex is brilliant at memorization. When Alex sees a question, they just absolutely overload the page with raw computer science facts. They dump every single piece of knowledge they have onto the paper. But there is zero analysis. It's just a data dump. Then, on the other side, we have Sam. Sam knows the material too, but Sam panics when the timer starts. Sam rushes, completely misses the specific command word requirements, and writes an answer that doesn't actually address what the examiner is asking for. Both of these incredibly smart students are going to lose massive marks, and their papers are going to be covered in red ink. But what if we approach these exams a completely different way? Today, we are going to treat these exam questions exactly like a paleontologist treats a fossil bed. We aren't just going to hack away blindly at the dirt like Alex and Sam. We are going to systematically, carefully uncover top marks by looking at some very specific tools. And our core focus for this dig? We are deconstructing Integrated Development Environment, or IDE, presentation features. We are going to dig through the question parts, layer by layer, and reconstruct the full, perfect answer. Let's get into it. Here is our excavation map for today. First, we will look at the presentation challenge. Then, core IDE principles. Next is the technical methodology, followed by avoiding common traps, and we'll wrap it all up with evaluative thinking.
Part 1. The presentation challenge, the surface layer.
So, let's start at the surface. Why do students find applying concepts to unfamiliar contexts so incredibly hard? Seriously, this isn't just me making a guess. This is a direct, repeated observation from the Cambridge Principal Examiner reports. You spend months memorizing the definitions. You know exactly what an IDE is. But then the exam throws a bizarre, completely unfamiliar business scenario or a weird robotics context at you, and suddenly, you draw a total blank. This happens because of what we saw with Alex and Sam. The syllabus emphasizes over and over again that top-performing students don't just regurgitate facts. Cambridge wants to see a connected, conceptual understanding that transfers seamlessly into these new, weird contexts. If you just act like Alex and throw raw facts at an unfamiliar context, the examiner's going to give you a very low score, because you didn't prove you know how the concept actually works in the real world. And if you act like Sam and ignore the command word, like confusing describe with evaluate, you are completely missing the target. We need a strategy to break through this surface layer, and we'll need a framework to do it.
Part 2. Core IDE principles, identifying the fossils.
Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. All right, let's identify our first major fossil, prettyprint. It sounds almost too simple, right? It's an IDE presentation feature that automatically formats your source code with consistent indentation and color coding. But do not underestimate it. Examiners are literally begging to see logical, structured reasoning. Prettyprint isn't just about making your Python or Java code look pretty. It is a fundamental functional tool. It enhances readability so developers can trace causal relationships and structure their logic without getting lost in a massive, terrifying wall of text. Think about how top students structure their computer science answers. They don't just write a definition, they use a specific framework to break down computer science-specific assessment objectives. Have you heard of the PEAL framework? It stands for Point, Evidence, Explanation, Link. When a top student talks about prettyprint, their point is what the feature is, their evidence is the color coding or indentation, their explanation is how it helps trace logic, and their link connects it right back to the specific, unfamiliar context in the question. That is how you turn a basic fact into an undeniable mark.
Let's look at our second key feature, our second fossil in the dirt, expand and collapse code blocks. This is a function that allows developers to hide or reveal entire sections of code. Why is this so critical for your exams? Because it literally allows you to tune out the noise. Imagine you are dealing with a massive sorting algorithm in your project. It's hundreds of lines long. Collapsing irrelevant subroutines lets you focus strictly on the specific logic you are trying to debug. And this brilliantly illustrates how top students make those cross-topic connections that Cambridge loves. They don't just say, you can hide code. They explain that expanding and collapsing code blocks is an essential part of the debugging process because it allows a programmer to isolate logic errors within nested iteration or selection statements. You're proving to the examiner that you understand how these presentation features actually impact the software development lifecycle.
This brings us to a massively important rule. Analytical depth is infinitely greater than superficial breadth. Cambridge's academic benchmarks require deep, considered reasoning. If a 6-mark question asks about IDE presentation features, a superficial answer, like our friend Alex might write, just lists pretty print colors, code, and you can collapse blocks. That is superficial breadth. A deep, analytical answer, structured with that Peel framework we talked about, explains exactly how these features integrate with other syllabus areas. It explains how using pretty print helps visually identify an unclosed string literal, or how collapsing a block helps isolate an infinite loop. I want you to mentally test yourself right now. If I gave you 30 seconds, could you spot an answer that just lists facts versus an answer that follows point, evidence, explanation, link? The Peel answer is the one that gets the marks every single time.
Part 3. The technical methodology, the excavation tools.
Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, welcome back. Listen very closely to this official examiner alert. It says students lose marks by not showing working. Even if your final answer is wrong, method marks can save you. This is the holy grail. This is the method mark strategy. Examiners actually want to reward your step-by-step analytical process. If you can clearly show how you are applying an idea feature to a problem, you are securing marks. This completely reduces your exam anxiety, because even if your final output or calculation has a tiny flaw, the examiner can see your logic. Remember Alex and Sam from the beginning? If they just implemented the method mark strategy, their red pen marks would instantly transform into green check marks. We need a blueprint to make this happen. We need a systematic way to extract those method marks from the dirt.
To guarantee those method marks, you can't just guess. You need a standardized sequence. Here is your 5-step procedural framework, your computer science success blueprint for tackling absolutely any unfamiliar coding context. Step 1. Deconstruct the question. What command word is it actually using? Is it state, describe, or evaluate? Step 2. Extract the relevant data from the scenario. What language are they using? What's the specific bug? Step 3. Select your analytical framework. In our case today, knowing we need IDE presentation features to solve the problem. Step 4. Execute with clear notation, showing all of your working out clearly on the page. And Step 5. Present your final answer using the exact, correct terminology from the Cambridge syllabus. Imagine a 60-second timer starting right now. Could you take one of your old past paper answers and rewrite it using these 5 steps? Because if you can, you are automatically jumping up a grade boundary.
Let's look at a direct comparison of what happens when you use that 5-step methodology. Superficial candidates simply list facts like pretty print colors code, providing zero context to the actual exam question. Top-scoring candidates, however, apply the principles directly to the unfamiliar context. Let's do a little find the flaw exercise mentally. If a paragraph says, the developer should use an IDE, pretty print makes it blue, this is good, where is the flaw? The flaw's everywhere. There's no depth. Now listen to the rewritten, top-tier version. Using pretty print's color coding in this specific binary search algorithm allows the developer to immediately spot the unclosed string literal on line 42, while expanding the main loop block isolates the logic error, preventing the array from sorting. See the difference? That is analytical depth in practice. That is how you turn a failing grade into an A star.
Part 4. Avoiding common traps, hazards in the dirt.
We went straight to the principal examiner reports to find the top 3 mistakes students make across these syllabuses, and here they are in our interactive workshop. I want you to imagine scanning a complex data table of student errors right now. You've got 60 seconds to find the trend. What's the core issue? Mistake number 1, forgetting to check for overflow and edge cases, throwing away incredibly easy marks. Mistake number 2, failing to check boundary conditions during execution. And mistake number 3, which is the massive trend we've been talking about, giving answers that lack the specific context given in the question. Think about how this ties into IDE presentation features. If you are writing a program dealing with an 8-bit integer, and you don't use your IDE's expand and collapse feature to carefully isolate your while loop, you are incredibly likely to miss a boundary condition error hiding inside it. When your loop runs one too many times, you get an overflow error. The examiner doesn't just want you to say, I'll test it. They want you to explain how the IDE helps you test those exact boundary conditions without losing your mind in the code.
Now, you might be thinking, How on earth am I supposed to remember all this under the extreme pressure of an exam? Here is a brilliant memory hack. Use the visual story method to encode these IDE presentation concepts. I want you to visualize a story right now. Picture a dinosaur. We are paleontologists, after all. Picture a dinosaur with brilliantly color-coded, perfectly indented scales. That is your pretty print. Now imagine that same dinosaur folding itself up like a giant accordion to hide from predators. That is your expand/collapse code block. Let's do a speed writing challenge. You have 30 seconds on the clock. If you sit down for the exam, recall the brightly colored accordion dinosaur. You will immediately remember these two crucial presentation features. You'll remember how they help you isolate those dangerous boundary conditions, and you'll be able to write that perfect peeled paragraph.
Part 5. Evaluative Thinking, Reconstructing the Dinosaur. To hit the absolute highest order assessment objectives, especially in the rigorous 9618 A-level syllabus, just solving the problem isn't enough. You must evaluate. Reconstructing the dinosaur means looking at the whole picture. Top-scoring candidates demonstrate very specific traits. First, they consider multiple solutions, maybe comparing different IDE debugging features alongside presentation features. Second, they analyze trade-offs. Third, they acknowledge limitations. What can't prettyprint do? It can't fix your bad logic. It can only highlight it. And finally, they justify their decisions with solid evidence. This is the complete computer science answering system. If you want to guarantee top marks, you need these 3 rules. Number 1, command word decoding. Number 2, rigorous PL framework application. And number 3, a strict time management matrix so you don't rush like Sam. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, @acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by.
Which brings us to our final, ultimate question for you to ponder today. Will you leave your method marks buried in the dirt, panicking like Sam, or info dumping like Alex, giving superficial memorized answers? Or will you use these exact tools, prettyprint, expand/collapse blocks, the 5-step methodology, and the POEL framework to reconstruct the full picture and show your true analytical depth in your next exam? The tools are right there in your IDE, and now they are perfectly organized in your mind. Drop a comment below with your target grade for computer science and the biggest challenge you're facing right now. Our team actually responds to every single comment. Like and share this video with a study partner. AC Exams, your Cambridge success starts here. Happy excavating and keep learning.